Morning, students. You're going to be watching a video today, taking some notes, and then doing your homework. I just want to give a quick shout out, say hello. I will be watching my daughter all day because our daycare got closed down for at least a day. We're going to find out more, but for right now, just watch the video and follow along. We're going to be doing some work on our calculator, so please, please, please make sure that you are using the calculator on your Chromebook or the calculator that you have in hand. And I'll walk you through those steps. Feel free to rewind, pause, or go slower through the video so you make sure you know how those calculator pieces work when we use them. All right, here we go. So if you could, go ahead and pause this video, and I'd like you to work through this problem. Think of it as a warm-up, and we'll go over it in just a second. Okay, so let's go over this. They're asking me to do the linear approximation of the following functions for f, and then use that approximation, use the linear equation to approximate f of 2.5. So here's the way I kind of think of this problem. They want me to do a linear approximation, which is a tangent line. But what do we know about tangent lines? We know that the slope is the derivative, and in this case we have the function f of x. So I need to find the derivative, which is the same as my slope, but now we're doing it at the value x equals 2. So we do know that x is equal to 1. Oh, I'm sorry, 2. Sorry, x is equal to 2, which means we can find what y is equal to. And that's the original function with 2 plugged in. And then we can find the slope by using the derivative. I'm going to hit pause and work through that. Okay, so I needed to figure out what was the output of the original function when x was 2. Just plug 2 in, do some simplifying, you get 4. Then I needed to find the slope of the function when x was 2. So I'm going to take the derivative, because that's what derivative is the slope. Take the derivative, and I'm going to evaluate that at the point x equals 2, and you can see we get a slope of -2, which means I can now write my equation of the tangent line. So what do we know? We know y1 is 4, I know x is 2, and then I know my slope is -2. Now, what I need to do is I need to solve this for y. I'm not going to distribute, and you'll see why in a second. There's no harm if you do. I'm going to add this 4 over to the other side, and then instead of calling it y equals, I'm going to call this f of x. This is the equation for the tangent line. Well, now I have to use that equation to approximate f of 2.5. And I'm going to put the approximate symbol, plug in 2.5 for x, and then we are just going to simplify. We get we get 0.5 on the inside, and then this is half of -2 is -1, plus 4 gives me +3. All right, so there's my final answer. That's the approximation. But let me just show you graphically, what did we just do? Because I think it's important for you guys to understand the whole idea of this. Actually, I'm going to grab a different graph. Okay, so let's take a look here. What I just did was I took Desmos and I typed in our original function f, and then I typed in our tangent line. And I just put in the point 2, 4, because that was the point that we saw. So let's just take a look at what's actually going on here, right? This tangent line can be used to approximate any value on the original function, but the closer we get to 2, the more accurate it's going to be. Now let's take a look at what we just did. We just found the value of 2.5. So if I look at 2.5 here on my tangent line, I can get as close as possible, but you can see the x value. There we go. 2.5 comma 3, right? Now, is that the actual value? No. If I look at the actual value, that's on this red graph. And if I can get close to 2.5, you can see the actual value is the 3.25. So I'm off by 0.25, and I have an underestimation for that function. So that's just kind of a visualization of why and how we can use this, just so you guys get an idea of how to think about this type of problem. Is the linear equation, the tangent line that we just found, is the blue line that can be used to approximate values that are close to the given x value. Right? Now, what would happen if I picked 2? If I plugged 2 in here, 2 minus 2 is 0, times negative 2 is 0, plus 4 is 4. I would get the exact same value. But as I move closer away from that, if I pick values that are further away from 2, they're going to be below the actual value. And you can see that the actual value would be on the red line. So what's the benefit to doing this? Well, I don't need a calculator at all to figure out my approximation because it's just a linear equation. But here, if I ask you something kind of crazy, it would be harder to do without a calculator. So that's why you can use the linear model to approximate answers. All right, we're going to go through a couple of items here that we don't want you to write down. This is just meant to be, let's use your calculator and see how this goes. This is section 4.1. It's kind of a review. We said we were just going to teach you how to do some of these and not really take formal notes on it. So how do I do the derivative in my calculator? Well, let's take a look here at this specific problem and see how our calculator can benefit us. To start, I'm going to just look at what does the equation tell me? We've got the number of fish in a pond, P of t, in a federal wildlife reserve after t years is given by the population equation. So this equation tells us the population of fish in a pond after t years. Well, the first question we actually don't even need a calculator for. And we'll look at the answer on a calculator, but we're also going to do this by hand. What if I want to evaluate the limit as x goes to infinity? And actually, this should be a t here because t is my independent variable. So what happens if I plug infinity in? Now, this is something that we can just plug infinity in. And if I do that, I get 60 over, now, e to the negative 0.2 times infinity is really just going to give me a negative infinity. And then as we saw last week, that whole e to the negative infinity is 1 over e to the infinity, which basically this whole thing is 0, right? So 0 times 19 gives me 60 over 1 plus 0, or 60 fish. That just tells me that if time went on for infinity based off of this model, there would be a maximum of 60 fish in this pond. All right, well, let's look at that on a calculator. So what I'm going to do is take my calculator, and I'm just going to type this into the equation. I'm going to go to y equals, and I'm going to type this function in exactly the way I see it. Quick reminder, if you don't know how to get the fraction, hit alpha y equals, and then option 1 gives me the fraction. So I have 60. I'll just press down or over. I'm going to do 1 plus 19 to get e, that's second ln. And then I got to go negative 0.2. And we use x instead of t here just because x is our independent variable. Okay, so I plugged this in. Now, if I just hit graph, on my graph, I know from the answer from number 1, I have to see at least 60 in the y maximum. So I'm going to hit window, and I want to see, let's see, I'm not sure how many years this is going to take, so I put 50. Could go higher. And then I'm going to go the y min. I'm not going to go negative fish. But then the y max could be 100. I put 80 because 80 is bigger than 60. So let's hit graph and look at what's happening. It almost looks like if your graph is on a normal window, you would think this would grow exponentially, but then something happens. It starts to plateau off, and there's a horizontal asymptote right here at 60. Now you could trace this function and just keep hitting over and look at the y values. As you go further and further, these are your x values, those are your years. The number of fish is getting closer and closer and closer to 60. And if we just kept going, we actually never truly hit 60 because it's the asymptote, but you can see that it's very close to that. Okay, so here's the benefit to doing this problem. I have this equation logged in as y1. Well, look at what y2 or number 2 is asking. Now it says, how fast? How fast is the population growing at 2.5 years? So what I'm going to do is I have to figure out the word fast is relating to derivative. Well, what I'm really going to do for this problem is I'm going to figure out without using without any work, I'm going to use my calculator, and I want to figure out what is the derivative exactly at 2.5 years. So you could do this by hand. You could either do a quotient rule or you'd have to do a chain rule if you rewrite this. But watch what happens. Grab your calculator, and I want to do the derivative. Now there's two options. We did say if we had the graph, your first option, if you're going to graph it, is go second calc. And then we're going to select option 6, which is dy dx. That's the derivative. And then you just type in the time that you want it. So I'm just going to type in 2.5, hit enter, and there's my derivative. Okay, so that's really friendly. Ooh, wrong button. There we go. All right. So if I was going to just take this answer, derivative part is the dy dx, and I'm going to round this to the nearest third decimal every time. And then we got to think about, well, what was this? The rate. This is a rate. It's fast. We're comparing the outputs, which are fish, to the inputs, which are year, so fish per year. All right, now that's one way to do this problem. And it's if you have the graph already. But what if we don't have the graph? I'm going to go second quit. There's another way to do this. So second quit gets me to a blank screen. If I hit the math button and I scroll down to option 8, it says n derivative. That stands for numerical derivative. You're going to hit enter. Now, here's the benefit to using TI-84s, is it has this very friendly notation. If you don't have this notation, I'll show you what it would look like if you have a TI-83. But I have to have d over dx. So I got to put in dx, so I'm just going to hit the x value there. Then you have an option. You could type this equation in exactly like you see it, or notice how we already put it in y equals? Since it's already in y equals, this is kind of a new piece. I could hit the vars button, which is right next to the clear. And then if I scroll over to the right and look at function, there's y1. So anything I put in y1 can be logged in. And that's just what I did, is I put in y1 here. And then I want the derivative at 2.5. When I hit enter, it gives me the exact same answer I did with a graph. All right. Now, look at the next question, if you can kind of see it. It says, how fast is the population growing at 30 years? Well, instead of retyping this, if you're doing multiple derivatives of the exact same function, hit second enter, and it just repeats what you wrote. Now, just go over here, and we want to type in 30, and make sure you delete anything extra, and then hit enter. Now, this is the rate that's growing at 30 years. Well, what about 100 years? Let's change it to 100. Right, so go second enter, and that'll take exactly what you wrote, change it to 100. And what about 10,000? I'm going to just go one extra step. What if I want to go further? Let's put 10,000 in there. Notice the rate that this pond is growing is basically 0. Now we kind of read this. This is scientific notation. We'd move 7 spots to the left. So this is basically 0 anyways. But I think that's kind of an interesting, cool piece here is this actually gives us a little bit of confirmation as to what we are doing on the original problem with the graph too. So we're going to skip the bonus question. And let's just take a look at what we just found. All right, I found the rate at 30 years was right here. All right, we're going to round to the nearest third decimal, which means we're growing by 0.515 fish per year. And then I had 100 years, which was this part right here. If I move this 7 spots, this decimal spot, I'm going to have 6 zeros here. That's so close to 0 that, what does that mean? It means we're not growing. Our population has remained the same after 100 years. And we saw after 10,000 years, the rate is 0 or close to 0. And does that make sense with our original graph? Look at the slopes. As I go to the far, far right, these slopes of the tangent lines are going to be basically 0 anyways. So that kind of gives us a little bit of information about this problem. All right, so that's one way. Actually, it's 2 ways to do it on your calculator. You could find the derivative from a graph, or you could do the math option 8, and that's the end derivative. So let's look at another problem that basically is the same thing. We're going to use our calculator here. Don't write any of this down. The daily cost, C, in dollars of producing X items is modeled by the function C of t equals this equation. It's a parabola. Find the marginal cost, C prime, if C prime is the cost of producing one item. So we got to find, basically, we're finding the derivative at 1. Well, in this case, I don't need a graph. I'm just going to go right to my calculator. I'm going to clear the screen, and I'm going to go second math. Oh, I'm sorry, just math, not second. And then we're going to select option 8. So I'll hit enter. And I want to do X because that's my variables. It doesn't matter if it says T or anything, you're still going to put X. Then you're going to type this equation in because I didn't put this into my Y equals. So I just want to put the exact equation that they give me into the function. I want to type it in correctly. So there's my equation. And then I want to tell it to take the derivative at 1. So this is basically finding the marginal cost at year 1. So that's $120.02. All right. Now, so 120 and I should say 20 cents. I said 2 cents. It's $120.20 to produce one extra item. All right. Well, what about to produce the 100th item? Let's find C of 100, and then we're going to compare that. Which one's more expensive, to produce the 100th item or the 200th item? And we're just going to compare. So here's how you can answer these questions quickly. We already did all the work in my equation up here. Since all I want to do is change the input, I'm going to hit second enter. And instead of doing 1, now I want to do 100. So make sure that says 100 for X and hit enter. And then I want to do the same thing for 200. So second enter. And then I'm just going to change that 2 to a 1. So it says 200 and then hit enter. All right. So if I ever want to evaluate a derivative at a specific point, and I don't have to show my work, you can use your calculator. So at 100, the 100th item costs $140 to produce. And then the 200th item costs 160. So which one is more expensive? We should write out a quick little answer saying that the 200th item is more expensive by $20 more than the 100th item to create. The big idea here, though, is to show you how to use your calculator to do derivatives. All right, so that's part one of today. It's just how to use your calculator. If you need to rewatch these videos, please do. The second part is now L'Hopital's rule. And we're going to go through a couple of problems here just really quick. If you want to pause the videos and try them, please do so. If not, pay attention here as we go along and take notes. So what do I have? I've got the limit as x goes to pi over 2 of secant over tangent. So what I'm going to do here is I'm going to evaluate the numerator. I'm going to use proper notation. All right, so we're going to evaluate secant at pi over 2. But before I do that, I'm thinking, all right, what do I know about pi over 2? Well, at pi over 2, that was going over 0 up 1, which means I know what cosine is and I know what sine is. But that doesn't tell me directly what secant is. So I'm thinking, wait a minute, secant is the same as 1 over cosine at pi over 2. And that helps me because cosine is 0. Well, in this case, I end up with a function that does not exist. So my numerator doesn't exist, but let's check the denominator and see what happens. Now notice how I am writing the limit of the denominator. You can't just jump to this part right here. You have to include the limit because that tells the reader what you're doing. Then I can do substitution, and I got to figure out tangent of pi over 2. Well, in this case, tangent is better thought of as sine over cosine. And then, wait a minute, we know what sine is. Sine is 1, cosine is 0, and this part right here is undefined. It does not exist. So I actually end up with does not exist over does not exist. Now this isn't directly a indeterminate form like we talked about, the 0 over 0 or infinity over infinity. But what it does say is maybe what if we check L'Hopital's rule then? Right? Can L'Hopital's rule be applied here? And what we're going to do is try the derivative of the top. All right, the derivative of secant tangent, and the derivative of 1 is 0, but the derivative of tangent is secant squared. Now, why is this a better form than up top? Well, what happens here is the secant cannot be divided by 1 and tangent. So we have this extra addition piece that kind of makes things not super easy. But when I take the derivatives of the top and the bottom, I notice I have a common factor because this is times. So I can reduce out a secant here, and that's going to get rid of one of the secants right here. Now, what you can think of then is this is actually kind of a trig identity. I've got tangent over secant. Now, I'm going to let you in on a little clue. Okay, hold on. There we go. Secant over tangent. I'm going to let you in on a little clue, right? If I plugged in pi over 2, well, the tangent of pi over 2 is undefined. We saw that. And secant of pi over 2 is undefined. So this doesn't really help us directly unless we do a little bit of a trig identity. So watch what happens here. What's a better way to think of tangent? Well, tangent, we saw here, was sine over cosine. So I'm going to just rewrite the top part as sine over cosine. All right? And then secant we know secant is 1 over cosine. Now here's the part where I want you to think of, if I rewrite this as 1 over cosine, I'm dividing by a fraction, which is the same as timesing by the reciprocal. All right? So then what happens? The cosines go away, right? Because we times by the reciprocal. And I'm left with a much friendlier limit, which we can actually do this very quickly. Sine of pi over 2 is 1. Okay, so that was just an interesting piece that could come up. It was L'Hopital's rule that allowed us to set up a trig identity that allowed us to evaluate the limit. You're not going to see a lot of those. I just wanted to bring that to your attention. What you are going to see are these next two problems, and you definitely want to take notes on these. So pause the video if you need to as we go through this. But what do we have? We have the limit of a function divided by another function, but this time it's f of x. And in the table, we are given the values of f and its derivative for the numbers 1 through 6. So we're going to basically follow the exact same form as we did before, but now instead of evaluating the numbers, we're just going to refer to the table. So I'm going to try to save some time here, and I'm going to take the limit of the top. And that's really friendly because all I have to do is plug 2 in for x, and I get 4 minus 4, or 0. And then I'm going to take the limit of the bottom. Notice how I'm not saying the entire fraction is equal to anything. I'm just evaluating the limit of the top and comparing it to the limit of the bottom. So this is just direct substitution. You can skip some steps here. You know 3 times 2 is 6. But now I have to figure out, all right, what is f of 6? I don't know what the function f is, but I have a table that says f of 6 is 2. So this becomes 2 minus 2, or 0. And when I compare, I end up with 0 over 0, which is my sign that this is an indeterminate form. All right, I have to show this indeterminate form because now I'm going to take the original function and we're going to apply L'Hopital's rule. And L'Hopital's rule is the derivative of the top, which that's a really friendly derivative, you get 2, over the derivative of the bottom. And then we're going to evaluate that limit as x goes to 2. We have to be careful here because we have a chain rule. There's an inside function here. So f is on the outside, the derivative of f, and we're going to keep the inside exactly the way it is. But then I have to multiply by the derivative of the inside. And if you're taking notes, you might want to identify that that's my chain rule. So there's the derivative of this part. And then we're going to do the derivative of minus 2, which is 0. I do not have to write that. And now I can confidently say that this 2 is going to stay a 2, which means I should be able to get my answer, so I don't have to do each one individually here. But now I'm going to plug in 2 into this function. So I get f prime times 3 times 2 is 6 times the chain rule of 3. So then the question is, what is f prime at 6? Well, there's my table. F prime at 6 is 4. So if this part turns into 4, we get 2/12 or 1/6. Right? Now, every once in a while, you could get, after you do L'Hopital's rule, you could get another indeterminate form. It might be infinity over infinity or 0 over 0, which means you would have to take the derivative again. But there it is. Okay, let's try this one really quick. Again, if you need to pause it, go ahead and pause this video, sketch the graph, but you're going to see basically almost the exact same type of problem we just did. The only difference is instead of giving us a table, we have a graph. But we can get the same information from the graph that we can in the table. Now, here's what I like to do. If I want to find any points, right, I can just find the location. So f of 6 is equal to 3. We know the point. But what I'm more interested in is what about slopes? Right? Anything from -9 to 3, but not including the endpoints, has a slope or a derivative of up 1 over 1, up 1 over 1, up 1 over 1. This is rise over run, so I know that the derivative here is 1. And then what about between -3 and 1? Right? If I go here, then I've got my derivative is down 2 over 1, down 2 over 1, down 2 over 1. So that's just -2. And then I know the derivative of this linear piece. So we go up 1 over 1, up 1 over 1, up 1 over 1. So any point between 1 and 9 has a derivative of 1. So those are the things I might need. I don't know how many I'm going to need, but that's just kind of a quick way to look at it. Well, let's go ahead and evaluate L'Hopital's rule. The first thing we're going to do is take the limit of the original numerator. So I have to write that out, and then I can plug in 0. Now, if I plug in 0 here, I'll get f of 0. If I plug in 0 here, 2 times 0 is 0. So then the question is what is what is f of 0? Now that's a point, right? There's no prime here. So what is the equation? When f is 0, its output is 0. So this becomes 2 times 0 plus 0, or the numerator goes to 0. Okay. Now I'm going to check, and this is not a divide bar. I want to make sure I don't think of that as division. Now I'm just going to check the bottom. And this is just a regular function. There is no f of x. I should note in the equation it says this is the graph of f of x. The only time we can use this part is if we're dealing with the f notation. But here, we're just plugging in 0. Which, simplifying that side, gives me 0. So when I compare, I get 0 over 0, which is my indeterminate form. Now, that's the ticket I need right here to do L'Hopital's rule. And L'Hopital's rule states you can take the derivative of the top over the derivative of the bottom and apply the same limit. Well, notice the derivative of the top, we have f in there. So the 2 out in front is a constant. That's going to stay. But then I'm going to multiply by the derivative of the outside. The derivative of f is f prime. We're going to keep the inside exactly the way it is. But then I have to multiply by the derivative of the inside, which is 2. That's my chain rule. Okay. And then the next piece is the derivative of 2x. Well, that's just 2. And on the bottom, this is just a power rule. The derivative of the bottom is 4 plus 8x. Now we're going to do the same thing all over again. I'm not 100% sure notice this. If I plug in 0 here, I'm going to get 4 plus 0, so I will get 4 on the bottom. So I'm okay with saying equals because I think this is going to work out. Now I have to plug in 0 right here. So notice this chain rule times the 2 out in front, that's 2 times 2 or 4. And then when I plug in 0 here, 2 times x is just 0 plus 2. And now comes the whole reason why we have this graph we need the slope at 0. So here is the spot where 0 is. What is the slope? Any part on this blue line has a slope of -2. Rise over run. So it's the table that told us, excuse me, it was the graph that told us that this slope was -2. And now we can do some real quick simplifying. We get -8 plus 2 is -6 over 4. We get -3 halves. Okay, so you can rewatch it as often as you need. Homework tonight is in Delta Math. It's 4.4 day 2. It's on L'Hopital's rule. Please make sure you submit a screenshot when you're done, and good luck.